Good morning, everyone. So today we shall be looking at some of the symmetry properties of the Riemann tensor. In our previous, one of our previous episodes or presentations, we had shown the Riemann tensor to be written in this form. We rewrote the Riemann tensor in this form. And from this form, actually, we could also derive the following symmetry properties, which we did rigorously then. We have this first one, which has to do with the interchange of the two, the first two and last indices. So, for instance, this and those were interchanged. You simply move them to this side and that to the other side. And here, at this point in time, we have interchange. We can call it odd permutation between the first two indices or last two indices. So, for instance, here, I could move the interchange between lambda, or make the interchange between lambda and mu, and I get a minus sign. Of course, starting from here also, if I had left lambda and mu alone and made the interchange between mu and kappa, you can see that that gives me another minus sign. Well, if I were to perform both at the same time, both minus signs cancel and we have that. And also we had this cyclic permutation, an equation which rewritten in this form gives us that to be equal to 0. Okay, now from this Riemann tensor, we want to find what we normally call the Ricci scalar. And the Ricci tensor first of all, then later on we shall move on to the Ricci scalar. The Ricci tensor is given in this form by contracting the first and third index of the Riemann tensor using the metric tensor in this form. So you can see I have lambda here and I have mu in this form. So, of course, we shall find out actually that this is the only way we could do this. So, for instance, from one of the properties we had here, now you can see that this particular tensor, rewritten by our first property, symmetry property, here, bringing mu and k in that order to come first, and lambda and mu to come last, just as we have here. Of course, this will imply, of course, that if we were to contract these two, you can see in the first contraction, for instance, let me take this little space here. In the first contraction, R mu, or should I say, G lambda nu, R lambda mu, nu k. This should give me R here. So I said I'm contracting this and that. So this gives me mu k. Now, but by this symmetry property here that I've performed, you can see, since we have already stated, so in order not to clog things too much here already, since we have already stated that this symmetry property here interchanges the first two and last two indices, you can see that if I also contract nu, of course the metric tensor is symmetric. In other words, G lambda nu is the same thing as G nu lambda. So if I were to contract this and that, and this with this, so I'll be left this time around with R k mu. So you can see that due to the equality of these two operations, that is making this equal to that, you can see that this R sub mu k, which is obtained by this particular operation here, is the same as R sub k mu. Sorry, I keep saying k, but you can bear in mind it's kappa just in case. So for the sake of convenience, I'm maybe calling it k from time to time. So R sub mu k is equal to R sub k mu. And of course, like I've said, R sub k mu is obtained from this particular operation, which had to do with changing this Riemann tensor by the usual symmetry operation we have already stated at first here. So with that, you can see that this is indeed equal to that. Let me come again. I said, if you were to use this to contract this particular tensor, the normal thing you will get is R sub mu k. But of course, we know that by this symmetry property, you can interchange these first two and last two indices. If you did that, this is what you will obtain. Again, if you were to contract this with this and that with that, you will simply get R sub k mu and not R sub mu k. So I hope that is clear enough. Moving on to the next symmetry property of this. For instance, we have, just like we've stated right from the beginning, I could have contracted, of course, which is what we do. So we could have, for instance, pretended or decide to contract this lambda and then mu. In other words, we want to contract the first two indices on the Riemann tensor. The Riemann tensor here, you have R sub lambda mu nu k. So what if we decide not to do it this way, but this way? In other words, we want to find out if there's any other way we could contract the Riemann tensor to obtain a Ricci scalar, which will have just two indices. If we were to do that, now you can take note that by a usual kind of a usual operation in tensor analysis, I could just perform an interchange between mu and lambda. This is possible again because they are all dummy indices here. In other words, wherever I see lambda, I put mu. Wherever I see mu, I put lambda. And that is what I get here. But then again, you should remember that the metric tensor is symmetric. So this and that are the same. If I did that, this is what I'm going to have. Now, remembering again that there is a symmetry property on the Riemann tensor, which we have stated right from the beginning, that when you interchange either the first two indices by that odd permutation or the last two indices, you are going to get a minus sign. So if I were to interchange mu and lambda right from this place, I'm going to get a minus. So can you see something here? This last expression here and this are all the same except of course for the sign. Like we said that g mu lambda is the same thing as g lambda mu. Now, but you can see that by this operation, I've been able to convert this r lambda mu or this r mu lambda nu k to the original r lambda mu nu k. So in other words, I have something being equal to minus itself. So that gives us simply 0. Now similarly, if I were again to contract the last two indices on the Riemann tensor, instead of the first two, that is nu k, whereby I have nu k here, again by the same process, interchanging nu and k just because they are dummy indices, and if we do that, we obtain this. Then again, on the same last two indices, I can interchange these last two indices to get a minus sign. Now, if that happens, you can see again, just like we had here, that this is exactly the same as what we started with. Now, we have something again being equal to minus itself. That again has to be equal to 0. And again, we can see that from this expression, that from this particular symmetry property here, this symmetric property whereby this is equal to minus that, equal to minus that, and plus that, of course, we've explained how that came about. Supposing I started from the left-hand side by multiplying with this metric tensor, g lambda nu k. Of course, we have shown what the first term here would give us. G lambda nu k multiplying this was the very first thing we worked out here, and that will give us r sub mu k. Now, of course, because of the minus sign here, this is equal to minus that, is equal to minus that, and finally it's equal to that. So it's the same lambda nu k multiplying the whole thing on this particular expression. Now, should that be the case, you can see that here we have lambda nu contracting lambda nu. So the two middle indices, you get a minus sign. And of course, the minus sign is simply minus that. And now you have again lambda nu, what is it called? Lambda g lambda nu contracting this first and the last index. So we see another situation here where we are contracting the first and the last index. Here we saw one where we contracted the two middle indices. We get again minus of that, right? And then this again, by the way, when we contract this, the second index and the last index. So what we did initially was to contract the first and the third. But now here we are contracting the first and the second and the last index. So in other words, all of them are all equal to either r mu nu, r mu mu k, or minus of it. Either r mu k or minus r mu k. This is what you get. In other words, so r mu k is the only second rank tensor that can be formed from the Riemann tensor. Now, supposing, of course, we decide to contract the remaining two indices, of course, the first procedure was we could have contracted, like we've already stated, either this and this or this and this. This is what we will do naturally. Now, but doing this for the second and last index, this is what we obtain. Finally, using another metric tensor to contract the remaining two, we obtain this, which is a scalar. So in other words, to obtain the Ricci scalar, you will have to multiply or operate on the Riemann tensor with two metric tensors in this order or in this form. Of course, again, as usual, you could have one of these operations performed on the Riemann tensor, whereby if we interchange lambda and mu, we get a minus sign. Now, if we were to have contracted, for instance, nu and k, of course, we have already stated right from the beginning, we've shown how all these are equal to 0 when you decide to contract them in that order. There's just either the last two pairs or the first two pairs like that. So if we were to do that, you get 0. So again, and also given the fact, so again, okay, just before I get here, so again it means that in order to get the Ricci scalar, it simply just has to be this way. So this is why we said also, only by the following procedure can we obtain the Ricci scalar. So you just have to go through this way to get the Ricci scalar. Anything else you do, like some other combinations like this, will simply give you 0. Now it turns out this last expression also, for any cyclic permutation, so if I were to add this and it cycles, this particular property here is simply going to give me 0. Of course, it's the usual thing. I can simply decide to keep, so the usual thing you get in tensor analysis, I can clean this statement so that we can see this explicitly. If I keep the lambda just where it is, so I can have this to be mu nu k, r here, lambda mu nu k. The next thing I'm going to have, of course, is to say plus. I take a cyclic permutation again. For all this, I'm going to be moving just the ones over there. So I have mu k mu and r lambda nu k mu plus again. So like I said, cycles, leaving the lambdas alone, mu nu and then r here, lambda k mu nu. If I were to add all this, take note again that by cyclic permutation, this, and this are all the same. And even though they are all combined, so by usual property of this totally antisymmetric tensor. So I can simply pull it out, this nu k, and what I'm left with is what is inside. Of course, I could add a fourth one, but then it will simply be repeating what I already had right from the beginning, I believe. So if I were to perform it again, I will have plus epsilon lambda mu nu k, which is already what I have here. So that is completely redundant. So in other words, I could have this to simply be the first one here, nu k, plus here, lambda nu k mu, plus again, lambda k mu nu. So you can see that what is left there in the bracket has already been said to be equal to 0 right from one of the symmetry properties that we have already derived in the previous presentation. So from that we can see that this too is 0. So we can't even get a 4-dimensionally contracted tensor by this method. Okay, so now we are going to be looking more again at the properties of symmetries that are associated with the Riemann tensor. Now in this case we have, for instance, in 4 dimensions, the Riemann tensor normally, just like we do know in every tensor analysis, for any object, for instance, any tensor object, if I have a tensor, say A alpha, in 4 dimensions, it will have 4 raised to the power 1 components. In 2 dimensions, it will have 2 raised to the power 1 components. In 1 dimension, 1 raised to the power 1, or 3 dimensions, 3 raised to the power 1. That, of course, the number of indices is always the power we have. So, depending on the dimensions you're talking about. For instance, also, if I have F alpha beta, in 4 dimensions, it will be 4 raised to the power 2. That will be 16 components. In 3 dimensions, it will be 3 raised to the power 2. So the Riemann tensor has 4 indices. So in 4 dimensions, you have 4 raised to the power 4, and that gives you 2, 5, 6. But some of all the symmetry properties, of course, reduce this number of purportedly independent components enormously to just 20. Of course, hopefully in one of these presentations we shall give a lecture on group theory. So hopefully when we get there, we'll try to look at some of them. But everything just summarized this way is this property that we have here. Of course, we could have obtained this from this particular one here. This property here simply states that this 2 reduces this number of components to 36. We're taking the combination of 2 out of 4 such expressions, timesing it by itself again to get 36. And also we have that this particular property that we have that has to do with the interchange of the first 2 and last 2 indices. This again reduces the number of components to 21. There are many ways by which you could see this, but then again, I'm trying to avoid technicalities. Not much of a trouble anyway. But again, looking at the third property, this reduces it finally to 20. Of course, there's an expression by which you could have obtained this directly out front. From this expression, for instance, this gives you again, so this has to do with some group theory, not necessarily that technical, but then this is a formula with which you can obtain the number of components for any tensor and also the dimension. Now, in the case of the Riemann tensor, for instance, here we have 4 indices, and in 4 dimensions, this you have 4 raised to power 2, that gives you 16 times 15 divided by 12, again that gives you 20. That is the number of components you have, number of independent components. All those components are not all independent, so that's why we're talking about this. Now, looking at them again, the Riemann tensor in 2 dimensions. Again, we are looking at this formula again, derived specifically for the Riemann tensor. So you can see that in 2 dimensions, I have here with me 2, that should be 2 raised to power 2, 4. 4 times 3 gives you 12. 12 divided by 12, you get 1. So we have again just 1 independent component for the Riemann tensor, even though we have many other such components, but it's always equal to either this, let's say for instance in 2 dimensions, that we're talking about just this component. So whatever component we get by the interchange, various interchange, whether even or all interchange or permutations of the indices on the Riemann tensor, which is this, you either get just exactly this or something like minus of it. So no difference whatsoever. Of course, we can see at this point in time, because of some of the symmetry properties we have, should any 2 of those indices should be the same, especially the first 2 or the last 2 in particular. If we have the first 2 or the last 2, you can see from this expression, we have already stated, so let me just use this, r lambda mu nu k, which is the same thing as minus r mu lambda nu k. You can see that these last 2 indices are untouched. So, but if the first 2 indices are the same, let's say 1, 1, nu k, minus 1, 1 again, nu k. Of course, you can see that nu and k could be anything. So, just for the sake of argument, let's take them to be 2, 2. Minus r 1, 1, 1, 2, 2. My point in this case is, as long as the first 2 indices are the same, I mean, you can see it doesn't make any difference whether I interchange 1 and 1, you just get the same thing. But then we get a minus sign. So in this case, this would simply just be equal to 0. So for any time you have any such 2 indices, either the first 2 or the last 2 indices being the same, you get 0. So that is why all such combinations as this all gives us 0. Of course, we have a very beautiful way to summarize this result, and we have that this, the Riemann tensor in 2 dimensions could be represented as this, having just 1 component. Now, where G is the determinant of the matrix represented by that. Of course, now in this case, it means that we could, from this formula, obtain for any of these particular components here what their corresponding values would be. It could be 0 or could just be equal to what we had to be this originally. So how do we work with this formula? We could decide for any of these indices, lambda, mu, nu, or k, to choose either lambda to be 2, both mu and nu to be 1, and the last one to be 2. So if we had to do that, it's just a matter of, okay, if I write this Riemann tensor as r sub 2, 1, 1, 2, it means wherever I see lambda here on the right hand side, I replace with 2. Wherever I see nu, I put 1, and for mu, I put 1. For kappa, I put what? 2. The same thing, minus lambda, I put 2 for lambda, kappa, I put 2. Mu and nu are both the same, 1, 1. And that is what you get, times what we had here originally. Now looking at this, of course, the metric tensor is symmetric. So G21 is the same thing as G12. And so, as you can see, these 2 are just a product. So we get this to the G12 squared. Minus that times R12 divided by this determinant that we have originally defined to be this. Of course, you can see that this is the same with this except for the sign. So if I pull out the minus sign out of this denominator, this is what I get. And these 2 factors on top and below cancel. And I get this particular combination to be equal to minus there. And this is actually one of the first combinations that have been written right from the beginning. Okay, now moving forward, we say suppose we contract lambda and nu on this Riemann tensor in 2 dimensions as we have written it as that. Of course, in this business, what you usually do is to choose one of the indices to raise. Because usually, of course, you cannot contract any two indices that are either on the same level, either below or on top, that is as covariant indices or contravariant indices. Both lambda and nu occur here as covariant indices. We will have to raise one all across the expression, and we have to choose one. We can't, for instance, raise lambda here, come here and decide to raise nu. No. So you can decide to raise lambda all true, or decide to raise nu all true. You end up with the same result eventually. So if we pick lambda, for instance, to raise, and this is what we have, for instance, here in this particular Riemann tensor on the left-hand side. Now by Onah'S, you can cancel the lambdas and then push the lambda back to where it was. This is what you get. Now again, at this point, we are raising the lambda on the metric tensor here, and that is what we have. So I'm using the same dummy indices for all of them, for a particular purpose, of course, because it will help me realize I can just pull that out or work without it. Or naively, you can say you can cancel them through. Now, on the second term here, you can see that I have a lambda also. So I raise the lambda on this particular metric tensor, leaving every other metric tensor untouched. And now looking at this, you can see that g sub alpha lambda is common here. I pull it out. Naively, you can see, of course, that we're cancelling them both, but lambda r, whichever way that works. But the normal thing is you pull this whole thing together with this factor to the left-hand side, this minus that. Then you have this times whatever is in the bracket. Everything should be equal to 0, and then you should get this to be equal to that. Or again, naively, you can simply just cancel and you get that to be equal to that. So what it means here, we have chosen to raise lambda, and that lambda has been replaced with what? Alpha. Alpha replaces lambda. So that is what it is. Yeah, but it's now raised actually. So we could decide if we want at this point to call it lambda all over again, but there's no point. So we can just say, since what we intend to set is lambda to be equal to nu, and alpha have taken the place of lambda, so we are taking alpha to be the lambda we are still talking about. So alpha being equal to nu equal to lambda gives us this. So in this contraction, you can see wherever I say lambda and nu, I set them all equal to lambda. Equal to lambda. So I have here r lambda mu lambda k, r mu nu k, and then g lambda lambda here, and this is what I get: g mu k minus g lambda k, g mu lambda times r12 at r12 over g. Of course, all starting from the expression here that we have here also. Now there's something here we have to take note of. We are talking about two dimensions. So whenever you have the metric tensor written in this form, it's always equal to the number of dimensions that you are working with. So for instance, in this case, when you raise the metric tensor, on the metric tensor, if you raise one of the indices, the temporal part always gets a minus sign, which changes it, and you have it to be equal to the number of dimensions of the space you are talking about. And here, since we are talking about two-dimensional space, n will be equal to 2. In 4 dimensions, of course, I guess this is already familiar to most. G lambda with lambda on top and lambda down is equal to 4. Again, because when you raise one of the indices here, you get a minus sign for the temporal part. But if you have the metric tensor just as it is ordinarily, you remember the metric tensor, what you get is minus 1, 1, 1, 1. That's the normal general theory of relativity convention, the metric used in general theory of relativity. The trace will give you 2. But however, raising one of these indices in this way gives you 4. But this is 4 dimensions. We're just trying to make a point. We don't need it in the next development. So all we've done so far is to have gotten this here to be 2. So I'll simply move forward with what I intend to do with this. So next, we're looking here at this expression. We are saying that this should be equal to 2. So all I have here is r mu k to be equal to 2g mu k minus, well, what do I have here on the second term? So I have g mu lambda here, g lambda k. So I can use this, for instance, to lower this index. And what I'll be left with there is g k mu times here r1212 all over g. That's by lowering this index using this metric tensor. Of course, this again is the same thing as g mu k. So this metric tensor is the same as that. Performing that difference, I simply get g mu k r1212 all over g. So in other words, we have that r mu k is equal to G mu K R1, 2, 1, 2 all over G. Now looking at this expression, we can decide again to contract mu and K. Of course, by the usual analysis, we always say that you can't just contract them to the two indices, given that they are both covariant indices. One has to be raised, and we'll have to choose carefully which one and stick to it all across the expression. Okay, now for the sake of argument, let me just choose K. So I can decide, no, for instance, okay, let me just choose K. For instance, if I decide to raise it, in the end here, what will matter, because by the end of the day, I will have to say that RG alpha, I can use after raising K, then I'll have here to be K, yes, and here this will be mu. This, by the way, of course, is the same thing as RK mu. We've shown that that is the same. Well, we've shown that before, that previously R mu K is the same thing as RK mu. And we already know also that the metric tensor mu K is the same thing as G K mu. So it wouldn't matter in this case because the matrices are asymmetric. So please, for the sake of argument, it's just to make this all serious or easy to grasp. This is K mu. It's the same thing as G K mu R lambda 2, 1, 2 all over G. So raising whichever one you choose to raise, but just remember, stick to whichever one you're raising. If, for instance, here I'm raising mu, this is alpha mu, this is mu, and this is going to be K. Of course, if I were to have lowered this index, then I'll be coming down to, sorry, this will be alpha. Then this is again G alpha mu, then G alpha again, this is going to be K, R1, 2, 1, 2 all over G. Yeah, so all is okay. So just like what we did here before, again naively, well, let me put it this way. Alpha mu, I don't want to do a lot of things naively. So G here, alpha K, R1, 2, 1, 2 all over G equal to 0. Of course, this we would want that to be 0, so we can take that alpha RK is equal to G RK, R1, 2, 1, 2 all over G. Now, what am I driving at with this? What I'm driving at with this is I have already raised the index mu. And by raising the index mu, it has been replaced with alpha, but raised already though. So this is K equal to G alpha K R1, 2, 1, 2 all over G. So since I've raised mu, and the mu has been replaced with alpha, so it's still mu in a manner of speaking, just like again we have done here. Remember, we raised lambda, lambda became alpha, and again we just moved on. So here, I'm going to set alpha to be equal to K. And to this, it means I'm really setting mu to be equal to K. So remember, because what we wanted to do was to contract mu and K. Doing this again, I have this to be R. Well, let me make that all equal to whatever I like. Lambda, both of them being equal to lambda. G, lambda, lambda, R is equal 1, 2, 1, 2 all over G. And of course, at this point, I can see, since I've already made a statement about 2 dimensions, that this is equal to 2. So this is 2, 1, 2, 1, 2 all over G. But R lambda lambda is just the Ricci scalar. This is 2 R 1, 2, 1, 2 all over G, which implies that R 1, 2, 1, 2 all over G is equal to capital R all over 2. So at this point in time, it means that my Ricci scalar, Ricci scalar just came into this expression, and the original expression we had, I believe, was this R lambda mu nu K, written here to be G lambda nu G mu K minus G here lambda K G mu nu exactly times R12 1, 2 all over G. Okay, so looking at this now, you can see that at this point in time, I have R12 1, 2 all over G. What we have just done is to show that this was equal to that. So this is equal to R all over 2 G lambda nu G mu K minus G lambda K G mu nu. In other words, we have been able to rewrite the Riemann tensor in 2 dimensions in terms of the Riemann scalar. The Riemann scalar in 2 dimensions. So that is what this expression gives us. Now we are just going to see what it will be in 3rd dimension. Okay, so in 2 dimensions we have that the Riemann tensor could be written in this form. It could be shown also that in 3 dimensions it could be written in that form. Well, by the same procedure, of course, by which we have established this. Of course, in 3 dimensions, you can see you'll be able to get 6 components, 6 independent components from this formula. That's what you're going to get. That's 6 times 35 over 12 should give you 6. So let us see again in the next presentation as we continue with the